Today we are starting a new unit involving lots of conversions, and we are going to be focusing on a mathematical quantity called the mole. And the mole is just like a really large dozen, if you will, and it's a grouping term referring to the amount of atoms or molecules in a particular sample. So let's go ahead and define the mole as a grouping term used to describe the number of atoms. And it's specifically the number of atoms in the given element's average atomic mass. And the scientist who figured out this relationship with the periodic table's mass is named Amadeo Avogadro. And so we call the mole amount Avogadro's number, which we'll talk about next week. But it's good for you to get familiar with his name. It kind of looks like avocado, but it's not. Avogadro. Avogadro's number is what we use to define the amount of a mole. And this relationship between the element's average atomic mass is really helpful because then we can calculate molar mass using it. So when we talk about this term molar mass, this is the mass of 1 mole of a substance. And Avogadro figured out that 1 mole of a particular element is the same as its average atomic mass. So if you would pull out your periodic table and have that handy, we're going to want to use that to look up some average atomic masses, which is going to be the same as the mass of 1 mole of that element, or its molar mass. So for a moment, let's just take a look at some different elements. If you take a look at hydrogen, that's our first element on the periodic table, look at its average atomic mass, and if you round it to the hundredths place, you'll get 1.01, or maybe the periodic table you're looking at already rounds it to the hundredths place. That is how many grams of hydrogen equals 1 mole of the number of atoms of that element. However, oxygen, if you look over towards oxygen, its mass for 1 mole is 16, or 15.999. It rounds to 16.00. That's how many grams are in 1 mole of oxygen. And the reason that these numbers are different is because each one of the elements has a different individual mass. If you think about, donuts compared to eggs, compared to flowers, each of them are generally counted in dozens. However, you would expect for them to have a different mass for the entire dozen because they're different objects. And so as we have different elements, their mass for 1 mole is going to be different, and it matches the average atomic mass for that element on the periodic table. So this can be really helpful because we can then calculate the molar mass. I'm going to shorten that to capital M, using the average atomic masses. So I'm going to put using the periodic table. PT for periodic table. For compounds, you're going to add the sum of all of its atoms together. So for compound, find the sum of all its atoms. Okay. And when we do molar mass calculations, we're going to round these to the hundredths place. Some periodic tables round to the thousandths, some round more, for the sake of not keeping tons and tons of significant figures and writing them to death. We're just going to go ahead and round all of them to the hundredths place and make it easy. So that's 2 decimal places. If you want to make a note of that, we want to round to the hundredths place. 2 decimal places, okay? And if the molar mass is the mass of 1 mole of a substance, grams per mole, or G/mole, is going to be the unit of molar mass. And so if we have grams and we have moles of a sample, we can divide the mass by moles to compare the molar mass of an unknown sample to the mass values on the periodic table. So we can do comparisons using this unit by dividing mass by moles and then compare it to the calculated value using a periodic table. Because we also see this word per, it can be used as a conversion factor and say that this is the number of grams that equals a mole. And we've seen in conversions, if we have an equality, we can use that as a conversion factor in order to convert between these two units. So we can use molar mass, or grams per mole, to convert between moles and grams. We're going to do an example of each of these with calculating, comparing, and converting down underneath. But first, I just want us to think through this idea of grouping terms with some common terms that we use to group certain numbers of things. So it's a word that describes an amount without actually being a number. So what term could be a description of two people in this picture? Hopefully what comes to mind is a couple. So this is a word. It does not actually have a number in it, but it implies a group of two. Number of years. We've got 40s, 50s, 60s, 70s, 80s. Term here, decade. That's implying 10 years. We've talked a little bit already about donuts. This is generally found in a dozen. There's our term. Number of dollars, maybe $1,000. Number of followers, this one's more of a symbol. Maybe you've seen a K or an M, or if you have a ton of followers, a B. But all of those imply a larger amount, right? B is our most amount of followers. And then number of atoms, our grouping term, this is our new one. It's our mole. So just like all of these other terms that we're a little bit more familiar with, the mole is just another term telling us a certain number of atoms that is the same as its average atomic mass. And we'll talk about how many atoms that actually is next week, but right now we're focusing on, it's just that number of atoms in the mass. And it ends up being the exact same for every element, which is really cool and was quite a discovery for Avogadro, which is why he is given the namesake for this number. So let's do an example of each of those uses for molar mass that we talked about in the top section. First, calculate. So whenever we calculate, we want to use the periodic table mass of each element. And just like we wrote at the top, we want to find the sum of all the atoms. So in our H2O, this is what we're going to be finding, we want to add up 2 hydrogens and an oxygen for all of their masses. So what I like to do when I'm finding molar mass is just list out my elements and then write down what their periodic table mass is. We already talked about hydrogen and oxygen. Again, we're going to round these to the hundredths place just to keep it nice and simple and easy to write down. However, in our numbers here, as written, this is saying I have 1 H and 1 O. I'm going to multiply this by 2 since I have 2 hydrogens, but only 1 oxygen, so I'm not going to multiply that by anything. And then I'm just going to total this up. So what will happen here, this is 2.02, I'm just showing my work. So I'm going to add 2.02 and 16. Little mental math there, 18.02. So the molar mass of water, 2 hydrogens and an oxygen, is 18.02, and then don't forget that unit, grams per mole. There's my calculation, and you can do that for any compound, you add up the sum of all the masses, and that's how much is in 1 mole. Now let's convert. We're going to use now the molar mass that we just found of water to convert 3.2 grams into moles. So if 18.02 grams is 1 mole of water, 3.2, that should be like a sixth of water, right? If you think about the math there. Let's set up a conversion, see if we're correct. So again, let's clean out the cobwebs a little bit on conversions. Whenever we are converting, we want to start with the given. And then we'll draw our little train tracks. And then we are going to use molar mass as our conversion factor. This is just going to be a one-step conversion factor. Grams of water in moles of water. And what this is saying here when we see grams per mole, it's 18.02 grams equals 1 mole of water, okay? So whenever you see the slash moles, that's implying 1 mole if you're writing it in a conversion factor form. So it will be 1 mole is 18.02 grams. And now we can do a quick division problem to convert. And we get, and we get 3.2 divided by 18.02, 0.17758, lots of numbers on my calculator. So what I'm going to do is I'm going to round this to my number of significant figures in the given. I have 3.2, that is 2 significant figures. So again, our learning is building on top of each other, so we need to remember things from first semester. Writing this with 2 significant figures will be my non-zero numbers. So I've got these 2 I want, and I'm going to round. So this will end up being 0.18 moles of water. Ta-da! Okay, and we were right. It's much less than a mole, and it's around that range that we were thinking. Definitely a decimal fraction of a mole. And lastly, comparing. So we have, in this example, an unknown sample with a certain amount of moles and grams. So we're going to find that ratio of grams to moles and then compare it to the molar mass of water and hydrogen chloride. We'll have to quickly calculate HCl. If you look that up on your periodic table, you've got H and you've got Cl. So together, the molar mass of hydrogen chloride is 36.46 grams per mole. And then we've already been working with water. Okay, so those are our comparison points. Now let's plug in our values here. We want to do grams and divide that by moles. That will give us a comparison molar mass. So I got 36.46 grams per mole. Based on the mass and mole ratio, this matches with hydrogen chloride. So my sample is HCl. It will always match with one of the given molar masses or one of your given compound molar masses if you are comparing. Okay, so 3 ways you can use molar mass: calculate, convert, compare. On page 4, you're going to be calculating and converting. So you'll need to calculate here and then use this space to do a normal conversion with the given and the find. And whenever there's a space for a chemical formula, that's just asking you to write the symbols. Sulfur is an element, so that would just be S. Molar mass for that would be pretty easy. Calcium nitrate, don't forget to do your crisscross method. So this would be CaNO3 and you'll find the sum of all of this. 1 calcium, 2 nitrogens, and 6 oxygens for calculating your molar mass.